YouTube transmission.
Do you see there my pointer?
Yes. Yeah.
Okay.
Okay, so I think we can get started. Hello, everyone. Welcome to another talk in our webinar series. This webinar is also being streamed live on YouTube. You can find the link on our website or access it on our YouTube channel, Linea NCTI. Today, we have the honor of having Dr. Andrea Buccino from the University of Buenos Aires. Dr. Buccino is a researcher at the National Scientific and Technical Research Council in Argentina, and also an assistant professor of the Institute of Astronomy and Space Physics at the University of Buenos Aires. Her main research interests are in radiation transport, solar and stellar atmospheres, cool stars, extrasolar planets, and also astrobiology. That's quite a mouthful. She's also a member of the HK Alpha and SPI HK Alpha projects, as well as the Mega Muscles collaboration. Dr. Buccino, thank you so much for being so kind and having accepted to give us a webinar talk today on such interesting topics. The floor is yours.
Thank you for the invitation. Thank you, Tasia. Thank you, Rodrigo. I don't need a presentation. I'm an Argentinian researcher, and I will tell you during this talk about our efforts in Argentina to try to understand magnetic activity in solar type stars and beyond, either from observation and models. So I will concentrate in particular in activity, in stellar activity, in the inactivity cycles in solar type star and beyond. So when we talk about stellar activity, our best known star is the sun. The sun, we can see it in detail. We can observe all the magnetic structures in the atmosphere, even in detail, spatially in detail, and we can observe it every day, every time. So we know very much this star. We know that each feature that we see in the atmosphere are connected, are related to the magnetic field that is generated in the stellar interior. We can see spots, coronal loops, plashes, bright zones in the chromospheres that are plashes. We can see the corona. The corona is a manifestation, clear manifestation of the magnetic field in the interior of the sun. So it depends in which wavelength we observe it. But now we know that these features are not always constant on the sun, that the sun presents a clear cycle, that the cycle lasts 11 years, more or less. And when it gets a minimum, we have no features or less features, very, very little features. And we have a maximum, the sun presents in its chromosphere more intense and more extended bright zones that are the plashes. So this activity is cyclic in the sun and is a consequence of the magnetic fields. The sun is easy to observe, so it was observed systematically from 1750, and the best activity indicator is the sunspot number, because the sunspot can be observed and can be counted in its surface and in the optical. So this is the best registry of activity of a star. We cannot reproduce this series of activity for there is no star that shows this registry of activity, because we cannot observe a single star every day, every time. So the sun is our best star. And it has a cyclic activity of 11 years, a short activity of 11 years, of a variable amplitude, because each amplitude is not constant. It has a kind of modulation, which is responsible for each 80-year cycle. We have, along the 11-year cycle, oscillations that are biannual oscillations. We know that other activity indicators follow the solar activity, for example, the flares, their intensity and their number. We also know that during a period of time, the activity decreased. There was a pronounced decrease in the activity. This period of time was called the Dalton minimum. It was a level of activity lower than the media. But there is an also famous minimum in the solar activity, that is the Maunder minimum. The Maunder minimum was a phase between these years, 1645 and 1715, that the sunspot number presents a pronounced decreasement. But one can see, okay, during those times when the sunspot number was not systematically observed, probably this decreasement could be an observation artifact. But other activity indicators shows that during that period, it's really the activity of the sun really shows a pronounced decreasement. I recommend this article from John Eddy, where it's a historical article where he shows the reports of that period that shows really that the solar activity get low. For example, the number of aurora reports were lower during that period, the Borealis aurora. Another one that is very nice is that during that period, for example, here you have the eclipses path, the solar eclipses path during that year. There were 63 opportunities of observing solar eclipses in Europe between those years, and only 8 eclipses paths go through zones where dedicated astronomers live. And so in those 8 eclipses, several reports describe a faint corona, a reddened corona, and the reddened corona is the chromosphere, and not an extended corona. So they didn't see a picture like that, because the corona was nearly absent, was too faint. Why? Because there was not solar activity, or it was very low, the solar activity. So another interesting point is that the reconstruction of the solar activity from carbon 14, sorry, carbono 14 in Spanish, carbon 14. The abundance of carbon 14 is uncorrelated with solar activity. When the sun is active, some of the galactic constraints are preventing from reaching the Earth. So less carbon 14 is produced. The carbon 14 is counted in the 3 rings. So if you see more carbon 14 was because the activity was lower. So here you can see that during the Maunder minimum, the abundance of carbon was greater. And it was the case near these years, but the sun wasn't observed during that year so systematically. So we know that the sun presents in its cycle, the solar cycle presents broad minimum, that they are common, that they are usual. How is generated this activity cycle? The most accepted model is a solar dynamo. The solar dynamo is a kind of machine inside the sun that maintains the magnetic activity. For example, you have a poloidal field, and as the sun doesn't rotate rigidly, it has differential rotation. The equator goes faster than the poles. So as there is the plasma is frozen to the magnetic field, the lines get deformed, and so from this poloidal film, you get this toroidal film, azimuthal field. But both effects, the alpha effect and the Babcock-Leighton effect, reconstruct the poloidal field. And then from the poloidal field, you have again the toroidal field, and then the poloidal, the toroidal, the poloidal, and so the magnetic field reversed. And so this activity is cyclic. It's cyclic. The alpha effect is related to turbulent motions in the convective zone, and the Babcock-Leighton effect is related to a meridional circulation. And this is a very toy model. This is a toy representation of the dynamo field. If we want to solve a solar dynamo model, here you have a picture of the differential rotation, how the lines get deformed, and then how they go to the surface. Okay, and then again. If you want to get an expression for the magnetic field, you have to solve this equation. The magnetic field, the evolution of the magnetic field in time, and the dynamic of the plasma, or couple equation, 3D equation with many parameters and physics. So it's very complex. Obviously, you don't do that. You can do that, but it's very, 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 very difficult. So you approach to that equation with the mean magnetic, when the mean magnetic field. You average the equation. You can, okay, it's very complex. An approach is to get a mean magnetic field. Here you have an axisymmetric approximation, because there is a cylindrical geometry in this case. So, and you have, sorry for the question, but just to tell you fast, you have the poloidal field of the stars of the poloidal field, where is the A vector, and the toroidal field. You can see that the poloidal field could be is coupled with the toroidal, and part of the source is the alpha effect. And here you have that the toroidal field has a source, the sharing, and an alpha effect. So two sources. So poloidal get toroidal, toroidal get poloidal, and so on. So I want to concentrate, on that term, on the sharing. The sharing, it's related to how the rotational, with the differential rotation. So in case you don't have differential rotation, you must think that this term decay, and so you only have this term to fit the toroidal field. But in the sun, the sharing is very important. this is the internal structure of the sun. You have the core, a radiative zone that rotates rigidly. You have a convective zone that has differential rotation, and between both zones, you have what is called the tachocline. The tachocline is a very thin layer where the gradient of omega is really high, and so the magnetic field really gets stronger in this zone, in this layer. This is the tachocline. So in the sun, the tachocline plays an important role. Just remember. So, but we have the sun. The sun is a fixed star that we can know best in detail. We can observe it every day, every time. We can observe it in spatial detail, but it's only one star with these parameters fixed. If you want to know about the stellar activity and to reconstruct stellar activity, we know to see other stars. Stars similar to the sun, stars brighter, younger than the sun, stars cooler than the sun, smaller, and stars with different internal structures. In that way, we can change the parameters, the stellar parameters, and analyze the activity along all these parameters: rotation, age, temperature, internal structure. So now we have questions. So these other stars, or do solar type stars in general, always present activity cycles like the sun? How do stellar parameters affect stellar activity cycles? And another question, do non-solar type stars, cooler stars, for example, present activity cycles? So trying to answer these questions, we first need an activity indicator, because we cannot count spots in the stars because we cannot see the stars in detail. So one of the best and the most extended activity indicator is the calcium lines, You can see here an image of the sun in this filter, and if you see a cat here, you can see the line core, and when you pass through a bright region, you see an emission in the core. So this line guarantees to be a good indicator of flashes of spots. So when you see a star, you see something like that, you don't see even a point, but you can get a spectra, and this is spectra of the Ioch Scorpii, which is it is a solar twin, and it was defined, the Mann-Wilson index, as the ratio between the flux in the center of this line normalized to a continuum. This index is very famous, and it's called the Mann-Wilson index. So in 1966, started the HK project dedicated to observe solar type star. This project daily observed several stars. There were 2,200 stars, and they measured the S index. So they could reconstruct, or they could obtain, a registry of activity of several stars. And they found that in this sample of F2K star, including sun-like star, they obtained that 25% were regular, 60% were cyclic, like the sun, and 15% were flat in activity. Probably some of them were in a Maunder minimum phase. Probably they didn't show activity like the sun didn't show during the minimum phase. And some of them, older paper, show that these stars were old and probably they lose their dynamo. They lost their dynamo, but some of them could be in a minimum phase. One lot of papers goes in time studying stellar activity. Many programs continue to study stellar activity. Here, for example, this paper is not published. It's an archive paper, and study the stellar activity, the activity cycles and the stellar activity in general of I don't know, I don't remember how many stars, but hundred of stars, with the HARPS spectrograph that was dedicated to hunt exoplanets. Nevertheless, they could study stellar activity with this spectrograph. They still do. Okay, here you can see the Mond-Wilson index in the sun, and you can see that it reflects, it's like the sunspot cycle. It's the same. You have less detail, but you have the same shape and the same length of the cycle. Okay, so here, don't worry, here is a last paper, a fresh paper, but so beyond solar type stars, what happens with it? Now we know what happens with solar type stars. They could be cyclic, irregular, or flat. So what happened beyond solar type stars? What happened with red dwarf? Red dwarf are popular stars now, or they get popular over the last 20, 15 years. Okay. Why? Because one of the points is that the habitable planets that are detected usually lately are hosted by an M dwarf. Because it's easier to detect a terrestrial planet around a red dwarf because it's smaller, because the relation between the mass of the planet and the mass of the star is greater in comparison to the ratio between the mass of a sun and the mass of an Earth. So it's easier to detect a planet around an M dwarf. Sorry, I'm playing with my hands and you don't see me. Okay, so it's easier. And they are frequent, and they are more frequent. Planet Earth around M dwarfs are frequent. So here you can see the probability of the frequency of planets along the mass of the host star. You can see that there are, most of the planets are around solar type stars. However, there are many planets around M dwarf. You can see here the mass of the host star against the mass of the planet. Here you have the Earth, here you have the M dwarf, here you have the sun, and you can see that the Earth are in general around M dwarf, and this is around M dwarf. And in general, these stars, these planets are habitable because they are warm planets. So they are in the liquid zone. So they are habitable terrestrial planets. Another point that make M star popular are that they present short-term variation in stellar luminosity due to flares. What is it? If it, for example, here you have light curve of an M star. The light curve shows, this is, thank you for Kepler, thanks to Kepler satellite, they could observe this star 11 months with a 1 minute cadence. And they observe 6,000 individual flare events. So this star presents 18 flares per day. M stars, because of the contrast between the flare and the luminosity of the stars, is an easy target to detect to detect flares event. For example, here with TESS, you have a statistic when you can see that the most flaring stars are in general M5 stars. So M star present flare, present terrestrial habitable planets around them. And for example, that's why they are interesting to study, because these habitable planets probably are not so habitable because of the flares. And another point is that the dynamo theory could change, or the dynamo model could change over this stellar class. Why? Because when we see the sun, when we talked about the sun, we talk about the Tacock line and the role of the Tacock line in the generation and the maintenance of the magnetic field. However, when we see M stars later than this mass, smaller than this mass, they are fully convective stars, and so they lose the Tacock line. So what happens when the star lose the Tacock line? Well, this paper was very important. This paper shows that Wright and Drake analyzed the X-ray emission, which is a coronal emission, and so it's related to magnetic activity of several stars. In gray, you have solar type stars. In red, you have M stars, not convective, and you have M stars in general, and in pink, you have M stars, convective M stars, fully convective M star, that are slow rotator stars. So here you can see that M star fully and partially convective, but also fully convective, present the same relation than solar type star. So fully convective stars could maintain an alpha omega dynamo. So the Tacock line, the lack of Tacock line, is not critical for a dynamo model, or at least for the dynamo operating, or for the dynamo model, which means that the shearing could be located in the convective zone. So that's why M stars are important, or are nice targets to study. Okay, so we have those questions, and now I have this question. Do fully convective stars present activity cycles? So a long time ago, and now I will talk about my work, a long time ago, in CASLEO, we started a program dedicated to observe M dwarf, not only F dwarfs, but solar type stars and M dwarf. This is CASLEO. CASLEO is an observatory in San Juan. Here you can see, here is Brazil, here is Chile, and here is Chile's here, and here is CASLEO. Uruguay. Okay, CASLEO is an Argentinian observatory. There we have in this dome, you have a 2-meter telescope equipped with a spectrograph, and we have systematically observed a series of stars. Here are the people related to this project. Now I'm in charge of the project, but he is the fundator. He founds the project. And this all the people vinculated who take their PhD under this project. So one of the main objectives of the project was to explore long-term activity near the convective limit. Here is the telescope, a 2-meter telescope, and here is the spectrograph mounted. It's not benchmark, the band of bench. Okay, here is the web page of Casleo. You can see this page. You can ask, or you can ask me if you need to get any observation. And here is our atlas of spectra. We have 22 years of continuous observations since 1999, 4 times a year, 150 observations from F3 to M5, and you can see there the spectra. They are mid-resolution spectra in this wavelength, in this range. Sorry, this is in Armstrong, and you can see here, for example, Barnard star spectra. Here, 18 Scorpii, Iota Or. Here you have Tau Ceti, Epsilon Eridani. This sample is composed by this star here. This activity, this quantity here is an activity indicator related to the Mohn-Wilson index that shows that is correct. Is the Mohn-Wilson index corrected in color? Sorry, in color. So you can compare different stars of different type, and you can see here that we have, in general, active stars, but we have M stars that are very active, active, inactive, and very inactive. Here is we have 12% of F star, 33% of G star, 34% of K star, and 21% of M stars, of M1 dwarf. So here you can see the spectra. We can observe the calcium line, the sodium line, the H-alpha line, all in the same spectra, all simultaneous observation of that. This project gives to the world, I don't know. This project gives many papers. These are the most cited papers. I will tell in detail later something about this paper. But here we have the first detection of activity cycles in M stars. So these papers are the first evidence of activity cycle in M stars. M stars are not easy to observe because they are faint, red. Remember that the calcium line are in the blue part of the spectra, so we need hours of observation to get one spectra of the star. So they are not easy targets to observe, at least with a 2 meters telescope. But we have time enough in Casleo to do that. So other works, other result from this project is that we get 2 activity cycles, 2 simultaneous activity cycles for AD Leo. You can see here the poor registry of activity. We detected these cycles also in photometry, not only in calcium lines. So you can see here the activity that we have. It's not the sun, so we don't have many points because it's very hard to get each spectra. You need time, too much time. Romina Ibáñez Bustos, she takes her PhD under my supervision. Now she is a postdoc. Studied during his thesis many M stars, and she studied in particular Aumik, which is an early M star with a disk, and she joined Casleo observation, points in blue, with other spectrographs. from HARPS, from FEROS, from UVs, or public spectra, and she built a more reliable time series, and she analyzed this series with the corresponding periodograms, and she obtained 2 cycles for this star of 5 and 12-year longitude. She published this result in this paper. It's a very fast rotator star, very active star, and she obtained a cycle for this star. Another target of her thesis was an M4 star, which is is a fully convective star, which hosts a planet, a terrestrial planet, but it's a slow rotator star. It's a very inactive star. She also repeated this work. She joined the Galileo spectra with the HARPS spectra, with the FEROS spectra, and she obtained this series. We have some holes, I know, but we analyzed this series with the corresponding periodogram, and she obtained a 5-year cycle for a nearly fully convective star. And another hit of her thesis was the study of this active star. This active star, GJ 729, is a very fast rotator star and a fully convective. And this star presents many flares. She could detect the flares of this series of activity, and she eliminated from the series to only get the activity due to the beat dynamo, not to the flare. The flare could mimic some part of the cycle. So, alter this part of the cycle. And she obtained from the analysis also 2 cycles. One of less than a year and the other of 4-year length. And an interesting thing that she did in this paper is that we analyzed the photometry, the Kepler photometry, in collaboration with Nuno Lanza and Sergio Messina, and we could obtain a map of the features in the stellar surface. And we obtained that the stellar spots, not the spot model, shows that there is no migration in longitude. And so there is no differential rotation, at least in the surface. Nevertheless, even in the absence of differential rotation, we also have an activity cycle. So this was a very important result. If we analyze how these points, this result places, not the result, this is the activity as a function of rotation only for M stars. I indicate here the position of the M star we study along the HK alpha program. And here you can see Proxima Centauri, which is out of the fit, GJ 729, which is out of the fit, and Ross 128, that is in the fit. We need a statistical error. So all the stars in the fit might sustain or might have a similar dynamo mechanism. But those stars that are out of the fit presents another dynamo. So the first conclusion is that early fast rotator, partially slow rotator, and fully convective DM star present a stellar activity cycle similar to solar type stars. The question is it a similar dynamo or it's another dynamo? And so we are working on building axisymmetric nonlinear dynamo to trying to explain these cases. But I won't show here the result because I have no result yet. I have one model and a time series results here. One of the hits of the most cited papers of the program is the study of activity of Epsilon Eridani. Epsilon Eridani is a near star, bright star, and Travis Metcalf lead this work. He built a collaborative time series of the Mann-Wilson index. Here you have the Casleo spectra, and he built a 45-year time series, so the longest series of a star. Yes, I know. Yes, the longest at that time it was the longest series of the longest time series of S index ever built. And from the analysis, we obtain we obtain 2 cycles also for this star and a broad minimum in that part of the cycle. Bonvitense, Erika Bonvitense, and other people also previously, Saar, Brandenburg, obtained that if you analyze the cycle period against the rotation period in solar type star with very well defined, very well determined cycle period, these both quantities are distributed in 2 branches. They are distributed in one branch. In general, the active stars are in this branch, and the inactive stars are in this branch. And the sun is between both branches. So it is called a middle age crisis star. And some stars are in both branches. An interpretation is that this star here presents an alpha effect in an alpha omega dynamo, but an alpha effect different from the alpha effect in this branch. But those stars that present a point in the active branch and in the inactive branch present 2 dynamos at the same time. That was the interpretation of this diagram. Here we have, this is our contribution to this diagram. That was the cycles detected for Epsilon Eridani in this work. So nice Epsilon Eridani because it presents 2 cycles. So what does it mean that it presents 2 cycles? 2 cycles are 2 dynamos, are 2 different dynamos. There is the question. So we try to answer the question with these people, with Laura Straiman and Fernando Minotti. They are physics. They work at Universidad de Buenos Aires. They built an axisymmetric nonlinear model for the sun, where all the parameters were constrained or try to be constrained from observation and derived from exact relation. What they did was to average the equation, and that was easier to solve. But if you want detail about the model, here you have some details. They apply it for the sun, and we apply this model on Epsilon Eridani. Epsilon Eridani, the surface differential rotation, what was a constraint of this model, was measured from most observation, a satellite that measured the spots that observed from a most light curve, and we obtain it is published the differential rotation profile. And so this was our observation constraint. And so we could obtain in this pandemic paper the magnetic field a long time in the surface. Here you have the three components of the magnetic fields a long time. We define a magnetic index similar to the Mohn-Wilson index, integrating the magnetic field in the line of sight. And with here you can see the time series of the magnetic activity plus white Gaussian noise. And you can see here that it presents a kind of oscillation that could be one of the two, or we don't know, cycles detected from observation. We also see here some brown minimum where the activity is still, the oscillation is still present, but the activity is lower, like a Dalton minimum in the sun or a Maunder minimum. If we analyze this series with the periodogram, we have two cycles, a 4-year cycle and a decadal cycle, similar that we get from the observation. But here we have 250 years of observations. If we analyze the alpha effect, we can see that we have a based alpha effect in the Tacocline line and an alpha effect in the surface. And the alpha effect in the surface is responsible for the longer cycle and for the minimum, the brown minimum. But the alpha effect in the Tacocline line is still present all the time. So the alpha effect is responsible for the short cycle, and the surface alpha effect is responsible for the long cycle and the minimum. So in this way, we could explain with only one model the two cycles and the minimum in Epsilon Eridani. Another interesting result, also related to solar type stars and to activity in solar type star, is this work, this post-pandemic work, with Matías Flores, who takes his PhD long time ago under my supervision, and he studied two stars. Now he's a researcher, and he studied a binary system of two stars that are very similar in spectral time, in rotation, the same history, but different level of activity, very different level of activity, both cyclic. He obtained a 4-year cycle from Z1 red, and from Z2 red, he obtained an 8-year cycle, but a very low activity. Probably an interpretation is that this star is like in a minimum, like in a brown minimum, but still cycling. So like this, we are seeing one star here and the other star here, probably, is our interpretation of the two stars that are similar. This is a nice laboratory to analyze the activity because they are stars of the same age, of the same temperature, of the same, with very, very similar parameters. So the second conclusion is that simultaneous activity cycles and broad minima in solar type star could be modeled by a typical alpha omega dynamo similar to a solar one. And the alpha dynamo, and the alpha effect, could be this couple or sought in two parts, one in the surface due to Babcock-Leggington effect, and the other in the Tacocline. Broad minimum are usual in general in stellar activity, and they not suppress short activity cycle, so the Taco-Klein cycle. So that's it. Well, thank you very much. Here you have my mail. Any question? Sorry for my English if I get slow but I'm getting nervous. Thank you very much.
Thank you so much, Andrea. That was very, very interesting. So now we have time for questions from the audience. I see that there are many people on YouTube as well. Feel free to write down your question and I'll read it out for you. And here on Zoom, if you have any questions, please put your hand up and I'll call out.
May I?
Yes, please go ahead.
So thanks, Andrea, for the nice talk. My question is, has there been any work trying to correlate the stellar cycles that are measured on the time scales of years with stellar seismology that usually measures temperature fluctuations, either radial or non-radial, on much higher frequencies, as I understand? Is there any correlation between these oscillations?
No, I don't know if there is a straight correlation. I don't know. I know that I are many works also from Travis Metcalf trying to understand the role of rotation from astroseismology observation performed with TESS and
sorry, Andrea, you're cutting up.
What? Sorry.
You cut up a little bit. Can you repeat?
Okay. Here.
Yeah.
Mm-hmm. Okay. It was the camera again. Sorry. Basilio asked.
Yeah, about the correlation between stellar seismology on higher frequencies, measuring temperature fluctuations, and this type of work that you people
yes,
do.
what I sorry, Basilio was your surname. Yes, I don't know if there is. I don't know in general if there is a straight correlation between the cycle and those parameters you mentioned, but I know that there are. Travis Metcalf was studying the role of rotation from astroseismology in cyclic stars and the evolution of the stellar cycle. I think that there is a correlation. I don't know now as a straight correlation to say yes that the stellar cycle period correlates with this parameter. I don't know now this answer, but it might be correlated.
Okay, thank you.
Yes.
I see Rodrigo has his hand up. Please go ahead.
Hi, Andrea. Thank you very much for this very nice talk. I have actually many questions and doubts, and it's very interesting. First of all, you showed many slides and you talked about dwarfs.
Sorry. Could you talk louder?
Oh, wait a minute. Is it better now?
No.
Yes.
It's hard to hear you.
Okay. It's not only me.
Oh, okay. I think I have to change my mic. Just a second.
Shout.
If someone has a question, okay, I see it. Is it better now?
Yes.
Oh, yes.
Okay, thank you. Well, let me start again. Thank you very much for such a nice talk. I have many questions, many doubts, and the first one is you showed us that there is that M dwarfs are very likely to host planets, habitable planets. And I don't know if I'm mistaken, but aren't M dwarfs very active in the ultraviolet
Yes.
range? So wouldn't this ultraviolet light kind of sterilize these planets?
Yeah, okay, it's a great discussion. UV radiation could change life, could constrain life, not only destroy. There is a paper in astrobiology from Aberbash, I don't know, that where she studied the flares. I don't know if it was from Proxima. I don't know, when she did some experiment to see what happens to microbial life under UV stress. So not all probably it would constrain the life and it could change the life, but it could also destroy the life. I agree with you. But also it could be a source of energy to generate biogenesis process. So not only destroy, it could be a good source, but obviously it depends on the star. If you have a moderate active star, probably it will have less flares. But if you have a star like Proxima, it has super flares. So a super flare would destroy life. Yes.
Okay. Thank you. I didn't know that. That is very interesting. And my other question is, I don't know if I misunderstood you, but sometimes it looked like you used spectroscopic data to study the solar activity cycles, and I don't understand why don't you use a photometry, or did I understood it
because
wrong?
it's more precise. It's when you see the when you use the photometry, you see spots and flashes together, and so
Okay.
the contrast is lower. When you observe the calcium line, you only see the flashes, and so you only see the active regions. So they are better indicator. They are more precise and more sensitive to activity.
Okay, so aren't many close by M dwarfs to make life easier?
Sorry, I didn't understand.
Aren't there those M dwarf stars in the nearby of the solar system to make life easier, or are they?
Sorry, to make life easier. Or...
Yeah, easier. Actually, you told us that it's very difficult to observe these M dwarfs because they are
to use photometry. Yes.
Okay.
Yes, but I think yes. We are trying to find better activity indicator in the red part of the spectra where it isn't so hard, where the signal to noise is better, and so it's greater, not it's better, it's greater, and so you need less time to get a significant sign of activity. But H alpha is not a straight indicator, a straight activity indicator, because not straight, I don't know how to say, but it's not a good activity indicator always. Yeah. That's it. Calcium is better. I love calcium lines. Yes.
Okay, thank you very much. Thank you.
Okay, thank you, Rodrigo.
We're a little bit over time,
okay.
So maybe we can take a question from maybe a more junior member, if anyone else has questions. I'll give it a minute. Okay, let me check YouTube very quickly. Okay, there's a comment on YouTube that says the seminar was really good. Magnetic activity cycles is a very interesting area. But otherwise, there are no questions. Okay, so if there are no more questions, we'll wrap this up. This presentation will be available on our website and on Linea's YouTube channel. Thank you everyone for attending, and a very special thanks to you, Dr. Buccino. Everyone have a great day, stay safe, and I hope to see you all again in our next webinar.
Thank you very much. Thank you all.
Thank you.
Have a nice
Thank you.
day.
Thank you all.
Bye.
Thank you.